I was much happier working on something that nobody else was working on, that nobody knew anything about at the time, but was really, really interesting. Discoveries in science are not, let's understand this completely and then make our discovery. It's, oh, I see a signal. How do I make the signal higher?
Yeah.
I turn knobs. Every question was a new question, and every answer was a new answer. Mm-hmm. And every answer led to a new question. And how exciting is that?
In this episode of the 632 Nanometer podcast, Xinghui, Misha, and Mike bring you a wide-ranging conversation with MIT professor Moungi Bawendi, 2023 Nobel laureate in chemistry, who pioneered the controlled synthesis of semiconductor quantum dots, the source of the Q in QLED TVs. They cover the exciting story of his discovery, the scientific and historical context, how alchemists made nanoparticles, flaws in today's system of research funding, and more.
What is the quantum dot? Could you explain why they're called dots? Why not balls or something else?
Well, let's first start with what is a quantum dot. A quantum dot is a small particle of a semiconductor, and it's small enough that the electrons, or the excited electron, the exciton that you create, is quantum confined. So that the electronic properties of excited electrons are size dependent. It's like a particle in a box. Why is it a particle in a box? For a particle that's a few nanometers in size is because that electron has an effective mass, which is much lighter than a free electron. So an effective mass of the electron in a, let's say, cadmium selenide semiconductor is about 1/10 of a free electron. And so, you scale from the hydrogen atom to a quantum dot, and you find that the quantum properties of that electron, need to be in a box of about 1 to 10 nanometers, and you still have those quantum confined levels.
Are those systems actually close to what grad students, when they just start the quantum mechanics course and they go through Schrodinger's problem of particle in a box, is it close to it?
Absolutely, it's exactly that. So, you give quantum dots as an example in freshman chemistry because qualitatively it behaves just like a particle in a box problem with a different mass, but everything else is the same.
And how did you come to this, the problem of the particles in the box or quantum dots? How did you get acquainted with them?
So let me answer your other question first. You asked me why quantum dot. So when the community, when it was born, with Lou Bruce and Alexei Ekimov and Sasha Efros and, that generation, they didn't call them quantum dots. I didn't call them quantum dots at the beginning either. We called them nanocrystals, nanocrystallized, nanocrystallites, nanoparticles, little particles, all sorts of names, but not quantum dots. That was Mark Reed, who is a physicist at Yale, who coined the term quantum dot to describe these objects. It's taken from the quantum well, the term quantum well, which is thin two-dimensional sheets of semiconductors, and this is a zero-dimensional piece of semiconductor. So, a well and a dot. A dot is like a zero-dimensional object, as opposed to a ball, which still has the idea of a three-dimensional object. And so you asked me, how did I get into it?
Yeah, how did you get into the field of quantum nanocrystals?
That was an accident of history, really. Lou Bruce, who was another co-laureate of this prize, this Nobel Prize 2023 in chemistry, had discovered the quantum size effect in small particles that he was growing at room temperature in water using cadmium sulfide, and that he discovered that in the early 1980s. And in 1987, I had been nominated by my PhD advisor, Takeshi Oka, for an AT&T Bell Labs fellowship for my graduate work, to pay for my, for the rest of my graduate school time. And part of that fellowship was the opportunity to spend a summer at Bell Labs. So I went to Takeshi and I said, I'd like to go spend a summer at Bell Labs. And, this is in the middle of my graduate career. So not every PI would be happy about that. But he would say, oh, yeah, sure, fine, no problem. And so, they send these CVs to the people at Bell Labs, the PIs at Bell Labs who are interested in mentoring graduate students. And Louis was one of them. And he chose me to come spend the summer in his lab. This was summer 1987. And that's how I got acquainted with quantum dots. And then after I graduated with my PhD in 1988, before that, I was looking at what am I going to do for a postdoc? And I thought I wanted to do ultrafast spectroscopy. So I interviewed with a few people, including my colleague Keith Nelson here at MIT, Steve Boxer at Stanford. And then I interviewed at Bell Labs. And at Bell Labs, I interviewed with a few people. Lewis was one of them, but there were other people. Because I just wasn't quite sure what I wanted to do, but I really loved quantum dots. And so, I had all these offers from these people, including from Lewis. And then I went back to Lewis because that was the most interesting thing that there was out there, that I thought, at least, because it was a brand new area where nothing was known. And so every question was a new question, and every answer was a new answer. Mm-hmm. And every answer led to a new question. And, how exciting is that?
So in your actual graduate work, were you working on a different project then, rather than quantum dots? What did your PI assign you to work on originally before you went for the Bell Labs stint?
Sure. So when I was a graduate student, I worked in two very different areas. I started my graduate career as a theorist, working on the polymer theory with Carl Fried, using tools like renormalization group to understand the thermodynamic properties of different kinds of polymers, rigid polymers, semi-rigid polymers, electrolytes, polymers that are charged. And then a few years into that part, I liked it, but I was missing doing experiments. So I switched groups and moved to high resolution infrared spectroscopy, gas phase infrared spectroscopy, motivated by interstellar observations, basically looking for molecules. In the case of Takeshi's group at the time, it was molecular ions, charged molecules that could be created and observed in interstellar space.
In the late 80s, what was so right now, if you're a researcher, you don't know what to do. It's very attractive to do something that has AI in it, right? Because it's a hot topic. So I wonder, probably quantum dots were not that at the time. So what was that at the time? Was it something to do with the Cold War, like Star Wars or something that Reagan was funding? Or what was the kind of like the default thing to work on if you didn't know what to do? Or like what was the thing that was like the siren of whatever the hot topic is at the time?
Oh, I don't remember there was a hot topic back then.
No, I'm kidding. Like, of course, quantum dots probably weren't, right?
No, they absolutely weren't, because nobody knew about them.
Yeah. So what was, I'm curious, like what was the hot topic? That's like what was the hot topic that you didn't?
I'm saying. I don't remember that there was a hot topic.
There was not one. I see.
So do you think that has changed over time, like these hype cycles and there being hot topics? Is that a newer development?
I think that the hype has grown stronger. I don't think that there wasn't hype about particular topics. I just think it's grown stronger. Because I remember coming to MIT as an assistant professor, and this was 1990. Buckyballs, had been discovered. And the dean of science at the time, Bergeneau, we had lunches with the assistant professors, just come in, and he asked me, why am I not working on carbon buckyballs? And I kind of looked like him, like he was crazy. Like, why would I want to work on carbon buckyballs when the rest of the entire world seems to be working on carbon buckyballs? There was nothing for me to stand out in that direction except get clobbered. So I was much happier working on something that nobody else was working on, that nobody knew anything about at the time, but was really, really interesting. The buckyball stuff all the interesting stuff, as far as I could tell, had been done. All the discovery had been done. So what was the point of me working on that?
Because it seems like, quantum dots or buckyballs, it's like different directions or objects from nanotechnology, which became, I think, a hype in like 2000s when a lot of equipment from semiconductor appeared at universities and people got access to that. But I don't know, at that time, was there a term of nanotechnology at all? Because you said there was like nanocrystals instead of quantum dots, you call them.
Yeah, well, the term nanotechnology or nanoscience didn't really become part of the lexicon until the mid-1990s, maybe 93, 94. This is when the National Nanotechnology Initiative was created. And then it became a thing. But before that, no, it wasn't a thing. And then everybody wanted to work in nanotechnology. So that was the hype, you know.
It's a good rebranding of chemistry, you know, like chemistry is already at the nanoscale for 150 years.
Yeah. So, you know, and in biology, all the lipids and everything, all these globular proteins, they're all nanometer size. So they all became part of nanotechnology. So suddenly a lot of people were working on nanotechnology, and they had been working on it all along, except they didn't call it nanotechnology.
Similar to machine learning and linear algebra or statistical analysis. So rebranding.
That was absolutely a lot of rebranding still going on. So what was the hype in the mid 1980s? You know, I just don't remember something like nano. You know, that just didn't.
Superconductors?
Well,
High temperature?
yeah, absolutely. But that was the big hype. Agreed. I don't remember when that was. Was it 1988, 1987? I forgot where that. You know, there's a famous APS meeting, which was like the Woodstock of superconducting, you know, where they kept adding talks and the meeting, and you know, ended up going all night. I don't remember which year that was. That was late 80s.
Maybe like coming back to nanocrystals, if you could tell us like a short story, because I have heard that Romans have used nanocrystals or nanoparticles for staining the windows. I mean, not the windows, but it was used for coloring the glasses, and then later Faraday. If you could bring us from the history, and then how do you fit in there?
So gold particles, little gold particles, nanoparticles of gold have been used through the centuries. You know, you talk about the Romans or the Greeks using, you know, basically gold particles to create the red color in stained glasses in transparent things, right? And then certainly in medieval times, the stained glass windows, the red again is gold particles generally, very small gold particles. The plasmon, you know, effect makes it look red. And Faraday understood that, you know, back in the 1700s, basically. But it turns out that the recipes for stained glass windows in old cathedrals, etc., also creates nanoparticles, and it's the composition and the size of those nanoparticles that determines the color. And that's what Alexei Ekimov, the third Nobel laureate, co-laureate, was interested in. And that's how he got into the field. That's how he discovered the quantum size effect. He was interested in understanding what gave color to stained glass windows, you know, other than red, which was already known to be gold particles. Now, the recipes for stained glass windows are complicated because, you know, there's a lot of extra things you add to the glass to help it flow better or so that it doesn't crack, you know, all these things. But along with all these extra things, there's a few elements, you know, like you put in cadmium or selenium or sulfur or whatever, you know, copper or chlorine, which are the important ones that create the color. Obviously, it wasn't exactly understood why in the Middle Ages. So basically what Ekimov did, he got rid of everything that was extraneous. Just kept the silicon, the oxygen, and the elements that were going to form what he thought were the color-forming centers. And using a small angle X-ray, where he was able to measure the size of particles in the sample, he was able to correlate then particle size of particular compounds with color, with spectrum.
How does the X-ray, when you take a small angle X-ray measurement, how does that, I mean, there must be a lot of background from the glass itself, right? Because it's mostly, probably whatever, 99.9% of the sample is glass.
Yeah, but it has no structure.
So it ends up being kind of like a fuzz, and then you get...
Yeah, and then on top of the fuzz, you have the small angle X-ray signal that tells you about the size of what you're looking at.
Mm-hmm.
So it kind of stands out, especially if you're using heavier elements than silicon, then they scatter the X-rays more than the silicon. Oxygen doesn't really cause a problem, you know. Silicon's not that heavy. So if you're using cadmium-based compounds, or, you know, cadmium is going to be a much better scatter of the X-rays than the silicon. And so if you have an aggregate of stuff that has cadmium in it, you'll see in the small angle X-ray signal. So his first, you know, he tried cadmium sulfide at first, but it didn't work because he couldn't find a recipe that made the small particles. But copper chloride is the material that worked first for him. And then so he wrote a paper in 1981 in the Soviet literature explaining that he had seen a quantum size effect in copper chloride in in glasses. Then he went about trying to understand the nucleation and growth mechanism of particles in molten glass. And that understanding, based on old literature, actually, that led him to be able to make other materials like cadmium sulfide or cadmium selenide, and to begin to study those as well.
And was this purely driven by curiosity about how these glasses were made, or was there also a goal application driven goal that he had in mind? Did he want to make other colors? Or?
It was completely curiosity driven. Yeah, it was just the interest of, what is going on here? How does the world work? It's like, human desire to understand what's around us. He was a physicist, pure physicist of the old school. He didn't really care about these applications.
Yeah, I'm curious nowadays, how would he fit
Write
it
a
into
grant
the paper,
proposal.
like introduction, put in the motivation, what are the applications, and
He would never get funding.
yeah, exactly, how to get funded.
Yes. In fact, Lou Bruce says that, Lewis worked at Bell Labs, and at Bell Labs, getting funded was pretty straightforward. I mean, you basically went to your department head, said, this is what I want to work on. And if you had a track record or that sounded interesting, the department's head would say, fine. And then you'd give a paragraph description of what you want to work on and you get money. But that doesn't work like that in academia. Right. So Lewis says he would never have been able to get funding for what he wanted to do in academia. It was just, this really amazing surroundings at Bell Labs that allowed him to really explore something very fundamental, completely driven by curiosity, and really go deeply at it without having to bother with having to motivate it with, some, although the way that he got to it was motivated by something very practical. So Lewis was, so Ekimov was interested in color glasses and in stained glass. Lewis, was working in the mid-'70s, late '70s, during the energy crisis under the Carter administration, the OPEC oil embargo. I'm old enough to remember what that was like. I was an undergraduate here in Cambridge during part of that time. And, there were lines of car at gas stations because you couldn't get gas, and I think there was a period where your ability to buy gas depended on where your license plate was odd or even at the last number. So it was a very different time. So there was a true energy crisis, a real energy crisis until OPEC lifted the embargo. But that was a wake-up call, right? It was a wake-up call for energy independence, and that was the birth of the National Renewable Energy Laboratories, because at the time, the U.S. was highly dependent on OPEC. No longer. People forget now that we're energy independent in terms of fossil fuels. But at the time, that wasn't true at all. And so there was a big push to find other sources of energy, to use the sun, the renewable energies, et cetera, not because of climate, but because we couldn't have access to fossil fuels. And so there was a lot of interest to create fuels through photochemistry driven by sunlight, which sounds really familiar probably, right? Hydrogen economy driven by sunlight.
Mm-hmm.
Yeah. So, 40 years later, we're still talking about the same thing. Yeah. There's been some progress, but
Just on something you mentioned before, that gold particles were frequently used like in antiquity to get plasmon resonances in red color. Is the reason that gold was typically used that it's very easy to work with, so pretty much like it doesn't oxidize, it has natural stability, versus some of these other particles that might not have survived the same type of, like, I don't know how they were preparing the gold particles, milling or something like that, or how would they get very small gold particles, and why was gold a default? Is it the stability or something else?
well, the stability of gold is, it's a noble metal. It's
Mm-hmm.
as opposed to silver, which oxidizes, more easily. But they didn't mill gold. It wasn't like they took gold and made it into little particles. So I was given many years ago a recipe from the alchemists on making lead into gold. And the recipe consists of, taking blood from, I don't know, a snake that just bit something, or a cow or whatever. You mix all these ingredients together, all these natural ingredients together, you know, and along the way, you add a little pinch of gold. But the whole point of the recipe is to adjust the pH and to have uric acid or whatever you need so that you make gold salts. So you dissolve the gold and you have gold salts. And then when you take that solution and you dip the lead in it, you're basically coating the lead with a very, very thin layer of gold from the gold that's in the solution. And then you take it out and it looks gold.
That's fascinating. That is very cool.
So it's those kinds of recipes, you know, that they use. Basically, they knew how to make gold salts. And then you just put that in the glass. Then you heat it up and then the gold reacts and aggregates and forms particles.
Okay, yeah, that's actually fascinating. It's very interesting.
I mean, they didn't realize what they were doing. Obviously,
Yeah.
it was all empirical. But humans are amazing in their innovations that they were able to do in those times without really knowing any physics or chemistry. Completely empirical, and they came up with some very detailed recipes that were reproducible on how to make things, you know. And maybe it took a little longer than what we might do today, but it's kind of in a way it's kind of like evolution, right? You know, they try something and something works and they tweak it around and it works better, and it's very Edisonian.
How did it turn to nanocrystals? So was Louis Bruce the turning point that he is like, all right, I would like to figure out how to make the colloidal nanoparticles.
All right, so let me go back
right
to my story with the National Renewable Laboratories and making fuels. How could you make fuels? Well, you have to capture the sunlight first, right?
Mm-hmm.
Semiconductors are really good at capturing sunlight and creating electrons, you know, excitons, energetic electrons, then can be used not just for electricity, but if you can extract those electrons at the band gap into a solution of molecules, you can do photochemistry. So that was a big push there, you know, understanding electron transfer from semiconductors to molecules in solutions to do photochemistry driven by the sun. And so he was using a new kind of laser at the time called a picosecond laser. You know, today we buy them for very cheap, but they were newly discovered lasers, right? Newly invented lasers. And he was watching the kinetics of electron transfer from the bulk semiconductor through the surface into the solution, trying to understand how fast that goes, you know, because in a way that those kinetics determine the efficiency of the chemistry, right? But he did a higher signal to noise. It's a surface effect. So if you want higher signal to noise, what do? You make the pieces of semiconductor smaller.
Oh, wow.
So you made them smaller and smaller and smaller, and there were recipes already out there for doing largely from Hanglein's group in Germany, who were really interested also in a kind of photochemistry, but they were creating the chargers using radiation rather than sunlight. So there was a whole field of radiation chemistry using small particles of semiconductors back then, bigger, and that's how he stumbled into it. You know, he was using cadmium sulfide as the semiconductor, and he was making cadmium sulfide from cadmium salts and hydrogen sulfide actually at the time at low temperature. And he was watching the particles. He was watching the color change overnight. He would make a sample, and then the next day, you know, it would be a different color, and you know, it was kind of irreproducible. And he thought, "Oh, what's going on?" But he had access to T electron microscopes, so transmission electron microscopes. So he was able to correlate his observation with what the particles that they were being formed. And at first he thought it was a classical effect. He thought it was just me theory. Me theory is what explains
agglomeration of particles.
Well, me theory is the interaction of light with microscopic particles. So me theory basically, it has to do with the fact that these particles have a high index of refraction compared to the surrounding. So it explains why, you know, sunset is red, right? Red light doesn't scatter as much as blue light. So he thought that the absorption that he was seeing, which was not structure at all, because the particles were really actually pretty bad. So, he saw this change in the absorption onset of this continuum of absorption with no no bumps in it at all, no features. So that, you know, that looked like scattering, right? It looked like a kind of scattering. It didn't have features in it. Very much what you'd see in me scattering. But the particles were too small, so he tried modeling it using me theory, and it just didn't work.
Yeah.
How small were those particles?
They were a few nanometers in size.
Okay, so they were already...
They should have been transparent, basically, in the classical sense.
Well, I mean, it was a clear and colored solution, right? Cadmium sulfide actually was very, very bluish or yellowish looking, right? And so he was surrounded at Bell Labs by people who were, you know, deep into quantum wells, you know, so all these physicists studying quantum wells, you know, which was starting to become really interesting for lasing, for telecommunication. And because he was surrounded by all these physicists, you know, he thought, oh, maybe this is a quantum size effect, you know, and then that's how he stumbled into it. And he was interested in how the quantum size effect then would affect the oxidation potential of the semiconductor, again, for the application of photocatalysis. You know, if you have a smaller particle of semiconductor, then the electron has more energy than if it's a bigger particle, and then you can then have a higher potential for oxidizing, or in this case, reducing a molecule in the solution and capturing the sunlight that way. So his first papers talked about all these things, about the absorption, the exciton, but also the ionization potential of the oxidation potential of these small particles, because he was motivated by that application. But very soon the application sort of was no longer the guiding interest. The guiding interest became what I was interested in when I joined his group, and then when I submitted my proposal to MIT was, you know, you have atoms on one end of the spectrum, of the size spectrum, and you've got a big thing of mass, you know, on the other end of the spectrum, the bulk material. The properties of the atoms that make up the bulk material are completely different from the properties of the bulk material, right? So somehow, as you put more and more atoms together, the properties of the bulk begins to emerge. How does that work? You know, what is that process as a function of more and more atoms do you get the bulk material? And that was really the curiosity part of the research. How do you understand the properties of materials as they change from molecular to bulk-like, to the solid state? And that was a guiding principle also for other people in a different field. So there was another field of cluster chemistry or cluster physics, where people were mostly metal clusters, where they were making clusters in molecular beings. You know, these were small clusters of gold or silver or whatever that had 5, 6, 7, 8, 9, 10 atoms, and they were watching the properties of these clusters change one atom at a time. You know, you start with one atom of gold, it has certain properties. You take 2 atoms of gold, the properties begin to change. Take 3 atoms of gold, you know, and then step by step, you begin to see the evolution of the change of the material going. And for metals, it goes much faster because you don't need as many atoms for a metal particle.
Was it done with some chemical solutions, or
So
some
this is a molecular beam. This molecular beam is in vacuum.
I see.
So you have a source of your metal, let's say, you heat it up to a vapor, and you pass it through into a high vacuum chamber in a hypersonic beam of some sort, right? And so as the vapor cools, it begins to aggregate, and then you start making little clusters, and then you can use essentially mass spectrometry to separate different size clusters from each other. They can use lasers or whatever to study then clusters that are all the same size, you know. And then for the theorist, if you only have 3 or 4 at the time, at least, if you have only 3 or 4 or 5, maybe less than 10 atoms together, you can actually do theory and do DFT calculations or whatever, and look what are the possible shapes for a cluster that has 9 atoms of gold. You know, there are many possibilities, you know, and then but some are more stable than others. And if you know the stable shape, then you can begin to calculate what the properties are. And then you find that there's some clusters are more stable than others, you know, energetically more stable, or their shapes are more stable. So you get all this beautiful basic science at the metal cluster level. That was happening at the same time as the little particles of semiconductors were being born. In fact, the first conferences that I went to like the Gordon Research Conferences or the other big conferences, they were all cluster conferences. There was a room full of hundreds of people working on gas phase, small clusters, with the, looking at the details of, this cluster with 4 atoms is shaped in a certain way, but, theory doesn't predict it this way. So what's missing in the theory? Really detailed analysis of these very small metal clusters. And here we are with these nanoparticles that now are nanometer size. They've got hundreds of atoms, completely other part of the size spectrum. And we're doing it in solution as opposed to the gas phase. It's dirty, they're ligands on it. It's like these people look at us like we're crazy. How can you understand anything in this dirty system, right?
Do you know Uwe Kreibich? He wrote this book by Kreibich and Vollmer on all of these clusters. And I saw one of his old cluster machines, and he was always advocating that you had to do it physically so you didn't have the ligands and so forth. Yeah, he spent his entire career on exactly what you're describing.
Right. And so it was a cultural, clash. The chemists clashing with the cluster physicists, right? That clash still goes on today in different areas, but chemists tend to make dirty things. And physicists don't like to study dirty things. They want to study things that are really pristine and well characterized.
Which can fit into their theories.
Which can feed into theory, yeah.
Yeah, we like spherical cows.
Right.
I'm also curious, so why was, you mentioned that the material of choice was this like 2,6 materials like cadmium, sulfur, selenium. What was it like the material which was available, or what was the idea behind using, what is special about cadmium, or what is special about the sulfide selenides? Why not other materials from periodic table?
Tellurides, for instance.
Sure. That's also kind of an accident of nature and an accident of the periodic table. Cadmium sulfide is just ionic enough as a material that it forms at room temperature. It's not particularly crystalline, but it forms at room temperature. If you take a 3,5 material like gallium arsenide, it's much more covalent. You can't make it at room temperature. You have to go to a much higher temperature to make it. You can't take, the 2 salts of gallium and arsenic and make gallium arsenide particles. It doesn't work. It just doesn't work. And so it's because it's ionic enough that you could actually make it. But still being a semiconductor. Cadmium sulfide turns out to be a little harder to study than cadmium selenide. And the reason for that is because it's once you get into the band gap of cadmium sulfide is around 500 and something nanometers, maybe 520. I'm making it up, but it's around there now. So you quantum confinement, and very quickly you go into the blue and the UV, and you can't see it anymore. You can't see if they're too small, you can't see the color. It's all past what the eye can see. But cadmium selenide, the band gap is around 720 nanometers. That's at the far red end of what the eye can see. Mm-hmm. And you quantum confine it, and you basically cover the entire visible spectrum. So now you can see all of quantum mechanics, the entire size regime, from the molecular, where you have what is basically a molecular cluster with maybe less than 100 atoms, maybe 40 atoms or something. That solution looks pale yellow. You still see it with your eyes. And then the bulk looks this very, very deep red color. Mm-hmm. And then in between, you got everything. And if you look at the fluorescence, you got all of the visible colors, come out in fluorescence. And that's why cadmium selenide became the go-to material, because it was so well suited to humans.
So when you joined Louis Bruce lab in Bell Labs, what was your first project? What kind of problems were you solving, and how did you end up developing the chemical synthesis of the nanocrystals?
Oh, sure. So, I can make this story as long as you want, because there's a lot of interesting things to it, at least interesting to me. When I came to Bell Labs as a postdoc, Louis, working with Michael Seigerwald and Paulo Vasados, they had invented a method of making the particles in what's called an inverse micelle, which is basically a water, soap, oil solution with a tiny amount of water in a solution of oil, where the soap serves to make little puddles of water, basically it's a detergent, right? So the soap surrounds little puddles of water that are on the order of nanometers in size, maybe bigger than nanometers. But the important thing is that when you add a cadmium salt to the solution, the cadmium ions go to the water. They don't like the oil, right?
Mm-hmm.
And then they get distributed amongst all these little puddles. And so there's a very finite number of cadmium ions in each puddle. It's a Poisson distribution, stochastic, etc. But it's finite. It might be 10 ions or 10 atoms of cadmium 2+, in on average or whatever. And so that when you add then hydrogen sulfide, which he was doing back then, or what Mike Steigerwald developed, which was to use the sulfur or trimethylselenide as the source of the selenium anion, it's the finite number of cadmium that you initially put in that restricts the size of the particle you make at the end. It's not the size of the inverse micelle, it's the finite number of cations. And it's room temperature, and what comes out is largely amorphous, misshapen, amorphous, etc. Steigerwald had realized that the surface of these particles was still chemically active. So if you introduce a source of selenium or sulfur at the end that's a molecule kind of like that has an organic group attached to it, in addition to a hydrogen group, or so hydrogen, sulfur, and an organic group, that molecule will lose its hydrogen, basically become sulfur minus, and then the organic group, and that will bind to the surface of the particle. And suddenly you have this particle of cadmium sulfide or cadmium selenide that's decorated with these organic groups. It's no longer happy in water, right? It's no longer charged on the surface. It's not happy in water. It'll come out of the little tiny bubbles of water into the organic phase. But the organic phase, if you're a chemist, you will realize the organic phase was made out of heptane or hexane, so it's not aromatic. And the surface of the particles, they had put phenyl groups, aromatic groups, and those aromatic groups were not soluble in the hexane or the heptane, in the aliphatic groups. And so the particles would then aggregate with each other and come out as a powder. You could take that powder and purify it, wash it to get rid of all the impurities, and redisperse it in a solvent that was more aromatic, but in particular you could redisperse it in a solvent made up of what are called Lewis bases. Lewis bases is a molecule that has a free pair of electrons that can donate those electrons into the surface of the semiconductor. In particular, they were using pyridine as a Lewis base. Pyridine has it's a ring molecule with a nitrogen that has this pair of electrons and donates into the surface. And what they found is that when they took these small particles that were growing at room temperature in pyridine and annealed it to try to make it more crystalline, so a higher temperature, you try to get the crystal to be a little bit better formed, that in the spectrum, there was a peak at 410 nanometers that would appear in the absorption spectrum. Fairly sharp peak. And it didn't matter what size particle you made. You annealed it in pyridine, and this peak would begin to appear. And they had no idea what that peak was. They didn't know whether it was a magic size, magic size particle that, because, the cluster people, the metal cluster people, they were magic sizes, They were much more stable than other clusters. So maybe we had some magic sizes there. It turns out that turned out to be true. Or maybe it was what we call the charge transfer species, which means that the absorption is really the light creates the electron on the molecule on the surface, and the whole stays behind. And that charge transfer species is always at the same energy because it's dependent on what the property of the molecule on the surface is. And they didn't know. So my job was to figure out, what is this thing at 410 nanometers? What is this thing? So I come in and remember, I was a theorist first, and then I was doing high resolution infrared spectroscopy in the gas phase. I didn't know anything about chemistry, really. Synthetic chemistry, but I loved it. I really liked it. It turns out I really like being in the lab mixing chemicals. I didn't know that, but I really liked it. And so I asked Mike Steigerwald, what's a Lewis base? I should have known because we teach that in freshman chemistry. But that was a long time ago, right? So I forgot. And he explained to me, it's the molecules that has a pair of electrons that can donate into the surface. Okay. So I asked him, so what Lewis bases do you have in your lab? And then there were phosphines and amines and all sorts of Lewis bases. And so I tried to see if I could reproduce this or different. If it was a charge transfer species, maybe there would be, by changing the Lewis base, you could have a different energy, right? Instead of 410 nanometers, it might be 450 or 500 or whatever, right? And so I tried like more than a dozen. So in the hood, I had like all these little vials, all cooking, at high temperature and to the reflux level until they boiled, to see what would happen. And nothing happened to almost all of them except for one pot where I used tributylphosphine. I had this bottle of tributylphosphine and I cooked them, and I was using very small particles of cadselenite, and so it looked yellow at the beginning. And then, I cooked it, and all the others kind of crapped out, so nothing. But this one, it kept going, the particles stayed in solution, and the yellow color slowly changed to orange, and then it slowly changed to red. Over the course of many, many hours. So I just kept it going. Then after a few days, the color just completely disappeared. So there was clearly some interesting chemistry going on there. So I reproduced it, but I didn't wait until it disappeared. I looked, what is this red color that happened? And it was bigger particles. And the crystal structure was much, much better than we had before. And you could begin to see fluorescence from what we call the band edge, the color of that first exciton from these solutions. Before that, we never had seen fluorescence from the band edge. So this was...
Were you checking for fluorescence, like with UV, or how were you?
That came after the fact, That came after the fact where I tried. There was a fluorimeter, so you just put it in there. I may even have used a handheld UV light and seen that there was color coming out. I don't remember exactly how I realized there was actual fluorescence coming out of the right place. Because before, the fluorescence was extremely broad, it was full of, basically it was defect fluorescence, all over the visible. So, wow, that was really amazing. So I had an amazing sample, and it was magic. In fact, my transparencies have the word magic on it because we really didn't know what was going on. And it didn't happen all the time. Like I said, the first time the color disappeared after a while. Sometimes it didn't disappear. Sometimes it didn't work,
So how long does it take to go from red to disappear? What was the...
It took a few days. I don't know why, Probably there was oxygen that was in the vial, and I made cadmium oxide, and that's why it disappeared. So anyways, I went home. So I had a material to work with because my job was to actually study the electronic properties. And I also found out that I kind of knew what that 410 species was because I could reproduce it without the pyridine at one point, a little later. But really the focus became on these beautiful particles. And I started to do some pump probe experiments using femtosecond lasers, which were just being used back then. Then I went home for Christmas, and ran out of that bottle of tributylphosphine. Ordered 10 bottles of tributylphosphine. They were waiting for me in January, and I started making samples, and it doesn't work. It doesn't work anymore. It just doesn't work. You put your yellow powder in there, and it doesn't change color. It doesn't work. I spend more than 2 months probably hitting my head against the wall, trying to reproduce, making these beautiful particles. And then Mike Steigerwald suggests, well, let's take an NMR of what's left over in that bottle. Good thing I didn't throw it out.
It's just the right dirt.
And it turned out it had oxidized because it was an old bottle sitting on the shelf for many years. It had been poked many times. Air had gotten in, and it was just like 20-30% oxide. So I bought the tributylphosphine oxide and mixed it in with the tributylphosphine, and it worked again.
So was it expired, the bottle, or what?
Yeah, chemicals don't expire,
Well, I mean, what
it's
oxygen,
amazing.
The
Oxidized, yeah.
stored for too long.
There's a septum on the bottle, and if you poke it enough, you have to take it out with a syringe, right? So if you poke it enough, eventually you get some
exactly
oxygen.
right. So you're a chemist. I can tell.
He is.
Because that sounds to me like close to the discovery of superconductivity, when the assistant of Kamerling Honors, he just fell asleep, and suddenly, I forgot which direction it was, but anyway, he noticed that transition. He was like, oh, what's going on? Why the resistance dropped down or suddenly increased?
Yeah,
It
so
got him
many.
to
So many of these discoveries are complete
Accidents.
accidents.
Yeah.
And it's basically being at the right place at the right time and realizing what you have, It's because I could have easily the first time ditched the whole thing, but perseverance.
Sounds like here the dirty chemistry helped you in a sense. Because if everything was clean as for physics, you're probably not going to see the effects.
That is correct. That is correct. And so then I did a lot of physics experiments, but I could only make one size at Bell Labs. Then I moved to MIT. And again, we tried to reproduce it.
Well, what do you think was did you have a theory for why the oxide was helping drive the size? It was the particles were growing basically. So
yes.
Did you at that point have any idea why?
The oxide was a different kind of Lewis base. Now the oxide has that oxygen with 2 lone pairs in it. So at the time we thought, okay, it binds a little bit stronger than the phosphine to the individual anions, and so it keeps them in supply, and it also dissolves the particle at the same time as it grows. So it makes this equilibrium between molecular species in solution and the growing particle. At least that's what we thought at the time. The other things didn't allow for the dissolution of the particles. So you had a particle, and then it just maybe annealed the crystal structure, but it didn't dissolve. But if you're able to dissolve a little bit of the particle, then you can transfer mass from one particle to another. And then the small particles will dissolve faster than the big particles. So you transfer mass from the small particles to the big particles, and that's what we thought at the time, which was probably correct. So I come to MIT and nothing works again. And I don't know why nothing worked. It could have been, again, different sources of chemicals for making the small particles to begin with. Maybe the water quality here when we, the ionized water is supposed to be clean, but there are impurities everywhere, right? Also, at Bell Labs, I could only make one size, something that had an absorption around 560 nanometers or so. That was really nice. And if you want to study the evolution of properties from molecular to the bulk, you need a size series. No way around that. So Chris Murray had joined my lab with David Norris and Manoj Nirmal. So I arrive in July 1990, and I can't reproduce anything. Then Chris comes, as a graduate student in September 1990, and I put him to work, and he can't do it either, But we really quickly realized that we have to do something different. Otherwise, my career is over. And in retrospect, I thought that process of nothing working lasted for years, but it turns out it was only a few months. So your memory is really terrible, right? Your memory is so bad. So by December of 1990, we had already realized that we had to get rid of So what I had done at Bell Labs was basically make tiny little seeds of cadmium selenide using this inverse micelle process in water at room temperature, and then taking those seeds and put them in an air-free mixed solvent, right? This tributyl phosphine oxide under nitrogen, heated it up and allowed for some dissolution, rearrangement of the atoms. And so this was the idea of then nucleation in water and then growth in the organic solvent. And so we realized, okay, water is terrible for semiconductors. This nucleation process that we did at room temperature, it's very irreproducible. Let's just get rid of the water part completely, and let's do nucleation in a different way and do everything air-free, do everything with organometallic chemistry as opposed to salts. And so that's what we did. That's how the hot injection method came about. Chris basically heated up the solution of tributyl phosphine oxide to high temperature. And a syringe had, in this case, it was dimethyl cadmium and bis TMS selenide. The syringe together at room temperature, they don't really react, but you inject them very quickly into this hot solution. They begin to react together to form cadmium selenide, forms the seeds. The concentration of the cadmium and selenium drops quickly because now you've used a lot of it to form the seeds. And then you have a slow growth process. And that was the hot injection using that. And it worked. It worked. There were some reproducibilities that we eventually figured it out. But I could still only make one size because the temperature turned out to be not high enough to make all the sizes. We could only go to 250, 280 degrees Celsius. And those tributyl phosphine and the oxide were very expensive. They came in little bottles from Aldrich, many hundreds of dollars each. And I didn't have that much money. And we knew that we wanted to go to higher temperature. And it turns out that
Why did you think that higher temperature would allow you to go to multiple sizes or like give you more
we
freedom?
had this intuition that we were stuck at that temperature because of the size. The size because of the temperature. I didn't have a good reason for it.
Just like putting more energy into the system, basically, or?
Well, higher temperature is always good for making crystals, right? And so that was the intuition. It wasn't any more than that.
Okay.
Right. A lot of what we did at the beginning was very Edisonian, very guided by sort of a gut feel, right? Not really guided by a scientific understanding.
So there were like two phases. One of them is when you create the seeds, like nucleation, and after that you slowly kind of anneal it, and the seeds would grow into nanocrystals. So which of the temperature did you need to increase? Like both of them? Or?
Well, both of them. Well, actually, the growth temperature was more important than the seeding temperature. So it turned out if you replace the butyl groups, which are 4 carbon chains, with octyl groups, which are 8 carbon chain, then you increase the boiling point of the chemical, right? That's well known in chemistry. The longer chains have a higher boiling point. So we bought trioctyl phosphine and trioctyl phosphine oxide. The trioctyl phosphine oxide is used in the mining of uranium. So it's extremely cheap. It's dirt cheap. It's made in the train load as opposed to little bottles. So, you can buy a barrel of trioctyl phosphine oxide. We didn't.
Now you got plenty of it.
So, but we still bought bottles, but it was much, much, much cheaper than before. And then it worked to get us to the bigger sizes. And so by adjusting the temperature and the concentrations, we could get the whole size series then, from the really tiny clusters to what was basically a piece of the bulk.
So what about the speed of injection? Because the very early stage, when you do the nucleation, so you said you changed the solvent to increase the temperature, but was there any other know-how or improvements in terms of how to make this seed like uniform? Or I don't know, were there maybe some other problems related to the nanocrystal growth?
So the understanding of why it worked, although we still don't completely understand why it works, the beginnings of understanding why it works, I think it's still a little debated, but there's more understanding of it. But at the time, it was really a gut feeling, and based on some old papers from the 1950s on colloidal growth, that it was known that under certain conditions, you could have colloidal growth resulting in very uniform colloids. So colloids are basically aggregates of molecules in solution. And so we knew that it was possible if we could find the right conditions, and you tweak things a little bit and you find the right conditions and it works. And it wasn't that, okay, we have to understand the process to find the right conditions. It was like turn knobs, you turn knobs and you find the right conditions, right? That's how science really is, right? Science discoveries in science are not, let's understand this completely and then make our discovery. It's, I see a signal. How do I make the signal higher?
Yeah.
I turn knobs.
Yeah.
Then I understand it. And then I can write a paper saying, I understand this, and therefore this is the process by which you make it better. That's not how it works.
Yeah, and this is one of the things we really want to stress to younger scientists in particular, because it's not how it's presented in textbooks. It's not how you learn about it. Like the actual process of science is quite circuitous. But at some point, were you worried that if it doesn't work, did you come up with backup projects, or was there no option to fail?
Well, okay, so this is the memory issue, right? So my older self thought that it took years for this to develop. But then I asked recently, right after the Nobel Prize, I asked Chris Murray, what was the timeline? And he remembered because he had notes. He kept better notes than I did. And he said, by December, he didn't even know how to take an electron microscope. He wasn't trained on the electron microscope yet. He wasn't trained on the X-ray diffraction. So he had no way to characterize what he had made yet. But the hot injection was there in December before he knew how to characterize the particles. That happened, he got trained on the TM in January and during IAP, which is our independent activities period here. And the electron microscope. And then he was able to, during 1991 was the part where he was now able to characterize. And that was the beauty of seeing quantum mechanics with your eyes. That was the beauty of cadmium selenide, because you didn't need any instruments to characterize it. You could just use your eyes. It was all visible. You could see with your eye how good the sample was, just by looking at the color. If it was a bad distribution, the color would be washed out. If it's a tight distribution, the color would be nice and saturated. You could use a UV lamp and shine it on the samples, and you could see the emission, and you could tell whether it was a colored emission or it was a white emission. If it was white, it was full of defects. If it was nice and colored, that's what you wanted. There's nothing faster than the human eye as a sensor to do that throughput, right?
So was this the work for which you received the Nobel Prize? Is it the 1993 JAX? Or
Yes,
or
that was the work. Because before then, the discovery of the quantum size effect was in, let's say, 1981 to 1982. Then it was written up in 83 by Lewis and 81 by Ekimov. There were 10 years between that and the synthesis. So during those 10 years, you really couldn't do very much detailed physics on the material, because it was, even by chemistry standard, it was really, really dirty, really awful. It was full of defects. It was amorphous. That's why Lewis thought it was me scattering, because there were no excitonic features in the absorption, and there was no fluorescence. And this synthesis allowed the formation of these really high quality samples that we could really purify to be of a particular size, with the size distribution being really narrow, less than 5% deviation in the radius. And that opened up a lot of things. So it opened up the study of the physics of the material as a function of size, but eventually it opened up all the applications. So 93 was the paper, and 95, 96 was the creation by many groups, including especially Philippe Giossine's group at Chicago and my group and Paul Vasato's group, of putting a shell on the particles to make these core shell structures to get the quantum yield to be even higher, to go from 20% to 50, 60, eventually 100% quantum efficiency in the fluorescence. The first real-world application in biology was through the formation of a company in 1998. So just 5 years after this report of the synthesis. So you see the timeline, right? You see the effect in 1981. Not very much happens. You get the synthesis. That's like a step function. And now it opens up all sorts of things. So Quantum Dot Corporation was started in 1998 to commercialize the use of fluorescent semiconductor particles, quantum dots. And now the word quantum dot appears because the company is called Quantum Dot Corporation.
Was it the spin-off from the university?
Yes. So it was started, the founders were myself and Paul Vasados and Shimon Weiss at UCLA. Paul was at Berkeley. And then two business partners, John Martin and another person. The name will come to me.
Before we move too far past this, what's the 5% variability between the particle sizes that was like considered a good place? Basically, that's like, okay, this is now, they're very close in size to each other and commercially viable and so on. Is there a kind of like physics limit or method? Like, is it a Poisson distribution driven thing, or like what is the kind of, what's the target? How do you set the target for the variability?
We didn't have a target. And there was a purification process as part of this 93 work where we were able to get rid of the biggest particles in the sample and the smallest particles. So we were able to narrow the size distribution even further. And the 5% is really was limited by our ability to do measurement in the electron microscope. Because there's a very fuzzy, you can't see where the end of the particle is in the microscope, especially at the time. Microscopes have gotten much better. But you have to, everything was measured by hand. We basically took this is before digital stuff, right? So we took a photograph in the microscope, you would take a negative. You would make a photo of it, right? And then you take a ruler and you go and measure with a ruler the size of the particle. That's the 5% error. So the size of the particle, the distribution may have been better. I just don't know. But it was good enough. It was so much better than before. And as it turns out now, what's good enough for many applications? Good enough is where the line width of fluorescence is not determined by the distribution, but by the intrinsic line width of the material. And so now that we've developed those single quantum dot sort of measurement technologies, we know that our distribution is so narrow that the line width of a single particle is the same as the line width of the ensemble. And you could probably get a better distribution, but there's no point. in that sense. And so, new materials, now it's become the standard. If you create a new kind of quantum dot, you look, what's the line width of the single dot? What's the line width of the ensemble? If the ensemble still is much bigger than the dot, you say, okay, we can do better with the chemistry. Let's keep going with the chemistry to get the size distribution better. And that becomes your metric, basically your gold standard, the line width of the single dot.
Did you keep any of these original samples? Are they still around? Did they precipitate? Are they in solution?
I have one sample of cadmium telluride. I know tellurium is one of your favorite metals. I have a vial of cadmium telluride that was made in the late 1990s. That's it. I have a little museum in my office here. And at the time, the vial was full. Now today, the vial is, because it slowly evaporates, but it still fluoresces.
Wow.
Yeah.
That's impressive.
When did you realize that there were applications? Like, did you know it before the experiments worked out, or is it something that really came after, like in the aftermath, you started talking to people and looking at, okay, how can you use this new capability?
It was in the aftermath, right? So,
like, was biology even on your radar actually when you were doing this?
No, not in 93, not in 93. But you're at MIT. You're surrounded by people that have all sorts of interests, and you talk to a lot of people, right? And what we had was a material that was quite bright in terms of the emission, very narrow emission, and more importantly, the absorption spectrum starts at the band gap into the blue uniformly. I mean, it just keeps on going up into the UV. If you have a dye molecule, the absorption spectrum mimics the fluorescence. So it has a finite range. So if something that fluoresces at 600 nanometers, you want to excite it. If it's a dye molecule, you excite it at 560 nanometers. If you try to excite it at 400 nanometers, the absorption cross-section just is very low. There's just no absorption there. But with the dots, that wasn't true. And this was right around the time that gallium nitride diodes were invented, right? Nakamura, working for Nichia, had discovered how to make gallium nitride diodes, a source of blue, cheap, blue light at around 450 nanometers. That was perfect for the quantum dots, right? Just perfect. And so that's really what triggered the idea of all these potential applications, that we had these sources of blue light. The dots were perfectly suited. And as chemists, we knew the size was similar to a biological protein, a big protein or something like this. I knew, and Paul knew, and Shimon Weiss was working on biological fluorescence at UCLA. But I was surrounded by people in my own department who do imaging of cells with dyes, right? And I've got this thing is multicolored that I can multiplex. So a dye molecule, if you have, at the time, you have 5 different things you want to label on a cell with 5 different colors, you need 5 different lasers to excite the 5 different colors, right? But if you want to have one laser, let's say a blue laser with the dots, you use one excitation and you just change the surface of the dot to label different parts of the cell. And in one go, you can multiplex in a way that I thought you couldn't do with dye molecules. And that really was the selling point for the application, something that's bright, that you can multiplex in a way you couldn't do with dye, and that perhaps was more stable to photobleaching, because dye molecules, if you excite them with light for too long, they sort of peter out, they bleach out. And the dots didn't seem to have that problem. So that was the impetus for going into the biological applications. And the challenge was, how do you go back into water? The birthplace for Louis Bruce was in water. Then we got rid of the water because water was terrible for the dots because it oxidized the surface. And now we wanted to put it back in water. That turned out to be quite a challenge. That's a challenge that we solved in different ways. And then the company was born during a bubble in startups because of the internet, the birth of the internet. There's a huge amount of investment in startup companies. It was easy money at the time. So it was born, and a lot of the work at the beginning of the company was how to go from the oil to back to water so you can make them biological compatible. And they solved that problem using a particular method at the time. The real application, which is very widespread today, is in displays. That's a much easier application than biology. That should have been the first application. But because, we were all chemists working with biologists as opposed to working with electrical engineers, we didn't think of it until. But I had a really amazing collaboration with Klaus Jensen in chemical engineering. And he had access to blue diodes from HP. And I remember I did actually most of those experiments myself, putting the dots in polymer and using an NMR tube to sort of shape the dots to be like a hemisphere, the polymer dot combination, and then putting that on top of the diode
Oh, wow.
and seeing the downshifting of the color from the blue to whatever the color was. And so I wrote a paper with Klaus on dots embedded in polymer to create white light. Because the other thing that was going on technologically at the time was OLEDs. It was the birth of OLEDs. So OLEDs, organic light emitting diodes, were born by accident in the late 1980s. And they hadn't achieved their commercial success that they have today yet. There were still a lot of problems with them. They didn't last very long, etc. And so people were really interested in creating lighting, white light from organic molecules, flexible white light, right? And so making white light was something that was in the air. So we could combine different colors of dots to make real nice white light. And so we talked in that paper that came out in the early 2000s in Advanced Materials. I forgot now which journal it was in. We talk about making saturated colors and white light with quantum dots. That turned out to be the paper that is the important paper then for making the displays, because the initial displays take the blue diode, the gallium nitride diode, as a source of light, and then you incorporate red and green emitting dots in polymer, and you downshift a portion of the blue light to have RGB in your backplane. And then you have your LCD display where you use the liquid crystals, individually addressed pixels of liquid crystals to create your image. It turned out to be the killer app for the quantum dot, as opposed to biology, which, it's still a product that's being sold, being used today, but it's not the killer app. It's not what made it from an interesting research application to a widespread technology. So we're two companies that basically were the pioneers in there. Both using MIT technology, and Berkeley and Nanosys used IP from all over the country, basically. QD Vision was born out of MIT. Both ended up converging on the same application, which was for displays. The first company to use quantum dots for displays was Sony in the 2012-2013 model year, using quantum dots from QD Vision. I had that TV in my office for 10 years, and I have one at home still. Sony wouldn't give me one. I had to actually buy one on sale from Amazon. QD Vision wouldn't give me one because they told me Sony wouldn't give them either. They had to buy them from Sony. So that was the killer app, and then Samsung at the same time, realized this is an interesting application, but cadmium is not the right element to put in a consumer application. In fact, I was surprised when Sony put cadmium in there, because I had met with Sony in the late 1990s, and they had a list of forbidden elements, and cadmium was on the list of forbidden elements. But it worked, and so they put it in there for that model year. Samsung had a large group that ended up making indium phosphide quantum dots. It's a 3.5. It's much harder to make than cat selenide. It's less ionic, so you have to go to higher temperatures. It's just a harder material to make as a quantum dot. But they figured out how to do it and how to make it nice and bright and more stable, etc. And so they then made TVs out of indium phosphide. They bought QD Vision, or the IP and the trademark from QD Vision. So QD Vision had trademarked QLED, QLED. And I think that the big reason why Samsung paid the money to QD Vision was to acquire the QLED trademark. Probably they didn't care about everything else. They just wanted the trademark. Because QLED looks like OLED, except the Q has a little tail on it. Mm-hmm. And then you've got LG selling OLED TVs, and you've got Samsung selling QLED TVs, So there's a great trademark war. OLED is not trademarked.
Now they can call them quantum
and then they use the word quantum TV, yes, yeah. So this was, from a marketing perspective, this was genius. Right? It also happened to work, but great marketing,
yes.
Right? Great marketing.
Do you know if they're still using hot injection to produce particles at scale for TVs?
I don't know the exact process, but I gather that commercially, I think hot injection is basically the way that certainly know QD Vision was making it using hot injection. I suspect the other companies are as well.
Was there when you were first coming up with hot injection, was there a competing direction, like lithography or something else to produce uniform sized dots?
So what we've been talking about are what in the community we end up calling colloidal quantum dots, made with chemistry. The physicists around the same time were beginning to make quantum dots as well, but in a completely different way, in a very clean way, as physicists tend to want to make things, by basically making what I call strain growth dots, where you have a substrate And on top of the substrate, you form a thin film of a semiconductor with a smaller band gap, but the growth is strained because the lattice constant is different. And what happens is at the beginning, you end up puddling up little islands of the new material on top of the old material. And the islands have the properties, the quantum confined properties, and those are also called quantum dots. And then you can cap the whole thing with the initial substrate material, and embedded then in your material are these islands of the smaller band gap material that have quantum confined properties, which then you can go to low temperature and study and do all sorts of incredible physics on that. Those are also quantum dots. And certainly in my career, I've been inspired, heavily inspired by those physics experiments, trying to reproduce some of them with our colloidal dots. But you can't use them to make TVs, those physics dots. You can try to use them to make lasers. You can do all sorts of things, really beautiful things with them.
Single photon sources.
Single photon sources, for instance, which we're also interested in making with colloidal dots. But they're hard to scale because they're made under very pristine vacuum conditions using molecular beams, etc., and BE growth.
If you were to make a vial of quantum dots using the hot injection method, like how many liters or milliliters would you need to cover that TV?
To make that TV here?
Mm-hmm.
Actually, I'm not sure. I mean, I don't think it would be that much.
It wouldn't be that much, right? Yeah.
No,
So
it wouldn't be that much.
actually, Samsung probably doesn't even need extremely large.
But no, but the companies that make, they make a lot of TVs.
Okay.
They make a lot of TVs. QD Vision had scaled up from vials to multi-liter vessels.
But it's still vats, like they didn't
Vats.
scale to flow chemistry.
No, so
for
we tried,
instance.
with Klaus Jensen, we did a lot of flow chemistry work. It turns out that when you do flow chemistry, the rate of flow at the interface is slower than in the center of the flow. You can make the flow chaotic to solve some of these things, but we were never able to make particles quite as good using flow as we did in the one-step experiment, the VAT experiments. Empirically, what I think you observe also is that as you scale the size of the vessel, the reproducibility and the particle quality actually goes up. And
It's the edge effects go away.
edge effects go away. Yeah, it's a surface to volume issue again. Right? The surface to volume ratio goes down, and so everything becomes being made in solution without having to worry about the walls of the flask.
If you have unlimited resources in terms of, let's say, funding, what project would you pursue right now?
Oh, I have a lot of things I'd like to do that I can't do. I would go back. So I had to sort of abandon is a strong word because I don't want to abandon it, but stop my research on bioimaging in the lab right after COVID, during COVID. I would take that up again and, really boost that and have a much bigger group working on bioimaging. Because I think that there's a big role for iron oxide nanoparticles as MRI contrast agents. It just needs time and money to get it to work. And I have neither. I don't have the money and I don't have the students.
What's
Students are the rate limiting factor?
Well, no, paying the students. All comes down to money.
Yes.
What's the fundamental need for contrast in MRI, and also what are the kind of different solutions that are possible? So what would be the unlock of having it work?
So MRI contrast actually works really well. If you have an injury, like a joint injury or something, you probably will get contrast. Contrast agents today are all based on gadolinium. It works really well, and the radiologists love it. You see a bright spot where you have more gadolinium than when you don't have gadolinium. You can see, all these things. But gadolinium is not a natural element that you find in the body. The early gadolinium contrast agents caused a condition called, NSF. It's kind of fibrosis, basically a lethal thing with very small fraction of patients ended up with this condition. And it turned out that was related to their kidney function. So if you had bad kidney function, you were much more likely to get this condition. So there was a black box warning from the FDA. So people with, kidney disease couldn't get contrast. That's been fixed to some extent, but there's still an issue with the nephrologists who don't want their patients to get a lot of gadolinium. And more recently, in the last 10 years, it's been realized that gadolinium also seems to be found in the brains of patients that have multiple contrast injections, like multiple sclerosis patients that need to be imaged often. their brain glows. You take an MRI of the brain and there's all this gadolinium in there. What does that do? We don't know. So right now it seems to be benign, but gadolinium is not that cheap either. And if you want to do targeted imaging, so right now contrast agents are not targeted. They're largely blood pool agents. They go where water is. But you want targeted agents, targeting, let's say, collagen or something like this. You're going to need a lot more quantity of these agents. You're going to have to inject more material than you do for blood pool agents. So the toxicity problems will go up and the cost will go up. You can make really tiny iron oxide particles to mimic the properties of gadolinium. This is something that we discovered with our collaborators, Alvin Jasanoff, for instance, here at MIT in bioengineering. Iron is not gadolinium. Iron is already in the body. There's already a lot of knowledge about iron oxide, and it's fairly benign. And if it's small enough, it gets excreted in the kidneys very quickly. It's not a problem. And if it doesn't, it goes to the liver. But the liver is full of iron, especially for pediatric patients. You don't want pediatric patients that need to be imaged often because of whatever illness they might have. You'd really like not to use gadolinium. And also from an environmental perspective, it turns out to be an issue. San Francisco Bay, Boston Harbor, Tokyo Bay, they have a much higher level of gadolinium than the ocean should have, right? And so there are fish there, and they drink and eat and all these stuff, and they end up with more gadolinium than you'd like. The Japanese are much more worried about this than the Americans, apparently. Because I go to Japan and they're worried about this. And I talk to radiologists here and they say, oh yeah, there's no problem. We love gadolinium. We know how to read the images. It's great stuff. Why would I want to change? So, there's this tension. But I think in order to convince people that iron oxide is a viable replacement, you need to work on it. You need to spend the time to do the animal experiments, the chemistry. It's going to take time and money. And I'd like to work on that.
It does sound like something the NIH would fund. Like this sounds
but NIH
really great.
NIH has become an agency that reimburses research. It doesn't fund proposals. It reimburses what you've done. You write a proposal, you have all these preliminary results. You've already done a lot of the research. And then you get your money.
What is your current funding mix like? Do you have a lot of funding from companies, from the private sector? Or
that's a really great question. So I would say my funding comes more and more from private companies. And the reason for that is the cost of research, it just keeps going up. It goes up faster than inflation in some cases, and especially the last 5 years, it's really gone up. As the primary cost of research here at MIT is the cost of students, salaries and equipment, but really day-to-day it's salaries. That has accelerated in the last 5 years. Postdoc salaries have gone up a lot, and graduate student cost of living in Boston is expensive, right? When I started at MIT, you could run a reasonably large group, reasonable group with 2 NSF grants. Now an NSF grant, if you're lucky, pays for 1 graduate student. Yes. And then no equipment, forget about equipment. And the success rate is much lower today than it was back then. And then you have to have done the work already, pretty much. You have to have a lot of preliminary results to convince referees, because the referees are so conservative. They'll find ways to tell you that it's not going to work unless you show them that it's going to work already before you get the money. So there is a crisis of funding from NSF and other federal agencies for fundamental research. Targeted funding from agencies is still okay. Very specific funding for very specific things. Congress will allocate, a set amount of money, and suddenly you have all this money available for something very specific. But unless you're working in exactly what they're interested in, then you have to go with the other sources. Inflation has eaten that up pretty much. And I talk to my other colleagues, we all say, how can this go on? This is not possible. It's not sustainable. Wow. 1 graduate student on 1 grant, now maybe 3/4 of graduate student, how do you pay for the other quarter? You get half a postdoc. How do you pay for the other half of the postdoc?
Yes.
You can't divide people in 2.
No. Yeah.
Right? But you're still expected to write a proposal that proposes to do as much as 20 years ago, but with 5 times less resources. It just doesn't work. It doesn't work anymore. And at some point, when you get to, instead of 3/4 of the student, it pays for 1/4 of a student, this just doesn't work. We have to rethink how we fund science, right? Especially at MIT, I think, because when we look at our competing universities, the cost of research at MIT is particularly high because we don't have a lot of graduate student fellowships. So you look at Stanford, they've built up a huge war chest of endowed graduate student fellowships. Princeton Chemistry subsidizes all the chemistry graduate students for the first 3 years. It's a huge, huge deal, right? So then they only pay for material and supplies from a grant as opposed to paying for. Then you can run the same project with a lot more students than I run with 3/4 of a student. How can I compete? The companies will still pay for the cost of doing research. So if I go to a company, I say, I need 2 postdocs, and they'll agree, okay, you need 2 postdocs to do this. And I say, each postdoc costs blah. They say, okay, and then they pay you blah, right?
Yeah.
They don't try to tell you, okay, the only thing I'm going to give you is, if you go to NSF, they tell you, I'm going to give you $150,000, and it doesn't matter what you propose.
Yes.
I'm going to give you $150,000.
Yeah, I hope postdocs and grad students would appreciate to hear that, how many efforts it takes from the faculty to secure this 1/4 of a student, and they need to basically pick it up from several grants, and you have that special opportunity to work here.
And places like MIT take a high overhead as well.
I'm really shocked to hear that from one of the most established professors at one of the most established places like MIT. It's like what others are doing and surviving in the field of academical science and research.
Yeah. Do you think that a place like, we talked about Bell Labs and how it's literally the opposite of this story, right? Like you walk down the hall, talk to one person, and basically they understand you and fund your project. Is there a place like that exists at this point for the kind of fundamental work that a lot of people get into science for, right? And if it doesn't exist, is there a possibility of recreating it? Like
that's a great question.
I think that's something
Bell Labs no longer exist. So places like Bell Labs really no longer exist. But Bell Labs was an anachronism of the fact that AT&T was a monopoly, which had a lot of problems. AT&T being a monopoly basically killed innovation in communication for so many decades. After AT&T was broken up in the 1990s, that was a revolution in communication. The cell phones came out. Yeah. When AT&T was a monopoly, you couldn't buy a telephone. You had to rent a telephone from AT&T. And everybody had the same phone, and the phone didn't change for 30 years because there was no motivation to make a better phone. That was terrible. But at the same time, it was a monopoly, so it could fund places like Bell Labs. And it didn't really care what Bell Labs did because its money came from running the long-distance network as a regulated monopoly. And it really didn't know what to do with what Bell Labs did. It was the cost of being a monopoly. The cost of being a monopoly for AT&T was to run Bell Labs. And they were, okay, fine, we make all this money anyway, so we just put a little bit of it as a tax to run Bell Labs. As long as you were doing something that could be tied in some way to communication, you could do whatever you wanted at Bell Labs, as long as it was interesting. And that's why it went away.
Yeah, you wonder, who's actually in this position now. It's maybe companies like Google, right?
Yeah, but Google isn't Bell Labs. Google is not a monopoly. Yeah. Google is driven by short-term profit. Google X, all these things that they're very focused on something that can become commercial in the 3 to 5 year range or sooner. They're not into long-term basic research.
And the same in universities. Like I feel like the topics move so fast. Like what I have done during my PhD, it doesn't matter maybe right now. And I think it depends on the grants, so that the fields move pretty fast, like not with the pace as it was back in the 80s, or when you have quite a lot of time to go deeper into the problem and find a solution for that.
There's a lot of interesting science that's being done in biotech startups because there's a feeling there that still there's some fundamental things that But it's still motivated by particular things as opposed to just curiosity driven. It used to be, when NSF actually funded research at a much higher level within the groups, that you could have enough resources to spend some of your time on stuff that was really just curiosity driven, because if there's enough money around, then you can spend some of that on stuff that you don't know where it's going to go. But when the money becomes restricted and you want to be able to renew your grant, you got to write papers. You got to have an output that's based on what you wrote in your proposal. it doesn't allow you to go sideways and, you discover something interesting. How do you fund that now?
Yeah, this is a discussion that I feel like comes up in so many different contexts. Like even with people that I know. So I'm no longer in academia. I work at a startup also that I co-founded, and just people that I meet that never even went into academia for fear of this issue, right? That they're worried that they'll kind of this magic of working on something that's more curiosity driven has been eroded out of the system. And it kind of, you can think about it two ways. Like either maybe we're in a period where this is at a low and maybe the curiosity driven funding and things like that will return, or maybe the opposite is the case, that we've evolved to a point where like maybe science is saturated and like curiosity driven stuff is no longer considered important because maybe it's less fruitful, like empirically, I don't know. It's kind of, like we haven't
I'm going to push back on that.
You mean like diminishing returns?
Well, like for example, we haven't had like, okay, has there been like a physics driven product, for example, that's been released in the last, 50 years, for example, like versus, applied physics or whatever, we haven't had a lot of new physics, driving maybe since radiation. I don't know. I
mean, the last 50
years.
Yeah,
laser,
so.
I guess. I don't know. It's like the laser is already pretty applied, right? So, but anyway, I'm just saying that it could be that
the quantum well lasers that were developed in the 1980s. That's
quantum
less than 50 years
lasers.
ago.
Yeah.
They're a multi-billion, trillion-dollar business. They're the root of communications today.
For sure, but I wonder if or at least I'm not arguing for this. Like I would love it. This is why I asked the question. Yes. But I wonder if the kind of like hard-nosed response to this would be that, okay, the way we make a quantum well laser is we give you like super focused funding. We already know what we want. We want to bet whatever, right? Yeah. Like this kind of thing. Maybe the idea is that model is actually working well, and like, MIT and all these other places are producing a lot of amazing research in these like very constrained kind of like applications focused. I would argue that not, in my opinion. I think actually what's happening is people are getting better at selling the results. Like, the headlines look good, but the substance has not improved from like focusing it on applications. But maybe because people have optimized the optics, it looks like, oh, if we focus on applications, we get more results, right? But I think there might be like from the perspective of people doing the funding or something, I have no idea. I mean, we should actually interview somebody that's on the other side of this, right?
It's the perspective of Congress.
Yes.
But Congress holds the purse strings.
But yeah, it could be that kind of by focusing on applications and all these, and kind of like forcing that from like the forcing function being, okay, we're going to tie funding to results and applications and actually results that you already have, right? Versus, which is I think one of the funniest thing you said in the interview is that NIH is reimbursing for research, which is kind of the feeling I've also had. We've applied for one NIH grant at the company where I work, and it felt like you basically had to have it finished before applying. Maybe that the people who kind of have driven these decisions would argue that, oh, look at all these amazing results it's creating. Now we have XYZ, all these startups coming out of academia and all these things. So I don't know. I wonder if this kind of motivates a future interview, I think, with somebody that's on the other side of the table. Yeah. But it's hard not to empathize with what you're saying. Like it sounds extremely rational.
The average time between invention and Nobel Prize in chemistry is 30 years. That's what it was for me. And the internet age has really not changed how long it takes to go from a curiosity-driven discovery to a commercial application. It's going to be 2 or 3 decades. Let's wait 30 years from now and see what we've killed. But we won't even know.
Yeah,
we won't even know.
That's the crazy thing.
We won't know. We just won't know what we're missing.
What if you hadn't worked on quantum dots? What area would you like? What's the road that you didn't take but you sometimes fantasize about? Like what would be the other area that you would have been excited to work in?
Well, I wanted to work in ultrafast spectroscopy. That was kind of new at the time, really, to use ultrafast lasers to understand the kinetics of mechanisms, at the femtopicosecond timescale.
Oh, attoseconds. You could have won a Nobel Prize in attoseconds.
Attoseconds, yeah. But I didn't.
And outside of science, have you ever thought about when you were a teenager pursuing a different career, or was it very clear that it would be science?
I was a violinist from a young age. Music would have been something that I might have considered ever so briefly when I was younger, but otherwise it would have been science.
Is there anything from your side which you would like to add or, I don't know, tell especially younger generations of scientists, engineers, chemists?
Even with all the challenges of funding that we talk about, it's still fun to be a scientist. I wouldn't trade it for anything. And you find your way. I mean, foundations are a way to get money these days. So the funding model may evolve. It's evolving. You find a way. Universities are going to find a way. There's enough money in universities. It's a question of priority. If it becomes clear that the priorities are just wrong, the equilibrium will come back. And you can see that like at Princeton or Stanford, where, they're willing to pay for graduate students, which is their biggest source of cost.
A follow-up question to that is, if you're somebody who's already in the lab and kind of maybe in a grad student or postdoc role or early professorship, how do you make sure that when something comes, like an accident, like a happy accident happens, how do you make sure to grasp it, right? Like what's the kind of how do you position yourself towards your research so that you can be the beneficiary of basically the
luck?
Just a search space, right? You're doing a search across some multidimensional space, and like how do you make sure that you don't miss the inevitable things that you'll find?
Curiosity. When something happens and it's not what you expect, why? Just don't dismiss it as being a pathology that's of no interest. Most of these discoveries are from effects that you don't expect. So if you see something that you don't expect, and it might be interesting, so pursue it. Just think about it a little bit. I often wonder how much. So when I was first an assistant professor and I was actually in the lab looking at data come out, I saw things that my students thought were artifacts or were not what they expected. And I saw them and I thought, this is a gold mine. And that comes with curiosity and experience, but mostly curiosity.
Thanks for tuning in for our conversation with the special guest, Professor Moungi Bawendi.
Great.
Thank you. This was fantastic.